Welcome back. I hope you had a good weekend. Last time we ended with a discussion of how our basic variables, the deformation gradient, the elastic and plastic factors of the deformation gradient, how they transform under superposed rigid body motions, and we had a discussion about that based on the notion that the energy and the dissipation should be invariant under superposed rigid motions. The reason we had to resort to those extra aspects of the definition of superposed rigid motion is because neither H nor K, nor G, the inverse of K, is the gradient of any deformation, right? So unlike the deformation gradient, which of course is the gradient of the overall deformation. So we had to resort to imposing additional criteria on a superposed rigid motion, and that led us to these conclusions here that H transforms just like the deformation gradient does, whereas K or G, its inverse, remains invariant under superposed rigid motion. So K can think of as a entirely referential tensor because of this property. Okay, we're ready at last to start talking about the idea of yielding the material. And from there, we will invoke a so-called work inequality of exactly the same kind that we adopted in our discussion of pure elasticity at the beginning of the course. And that will lead us to some interesting conclusions about the manner in which the plastic deformation can evolve. So first of all, let's talk about yield. So in our intermediate state, remember we stipulated that the material is in its sort of pristine natural state. So a crystalline material, for example, would adopt its perfect crystalline lattice structure in the intermediate state. And H, the elastic factor in the deformation gradient, is what distorts that pristine state and then embeds that into the current configuration at time t. So the elastic part of the deformation you can think of as being responsible for the distortion of the lattice in the case of a crystalline material. And you can imagine then that, okay, we could say that the material will yield when that lattice is sufficiently distorted, because the distortion of the lattice will give rise to stress. And when that lattice distortion or the associated stress reaches a certain threshold, then the material will yield in the sense that plastic evolution, which we defined as the onset of a non-zero evolution G dot of the plastic deformation, that threshold defines the state when this becomes possible, first becomes possible. So we can suppose we have a yield function. We could take it to depend on the elastic part of the deformation for reasons we've just indicated, depend on H. Then if a yield function should be then a constitutive function, and so should be frame invariant, which implies it should be invariant under superposed rigid body motions in particular. So the yield function at H, for example, should equal the yield function at QH, where Q is any rotation. And we know from what we've done before that the necessary and sufficient condition for that to be true is that the yield function should depend on H via, say, the elastic strain, 1/2 H transpose H minus identity. Or equivalently, on the elastic Cauchy-Green deformation, H transpose H. That's equivalent to the elastic strain. So I skipped that step here. A more primitive hypothesis would be the yield function, whatever it is, depends on H, should satisfy frame invariance, and therefore be expressible in this form. Okay, so the idea behind this is, well, this function then defines a certain threshold, a surface in a 6-dimensional elastic strain space. And when the distortion of the lattice, the elastic strain, reaches that threshold, then we can have an evolution of tensor G. This is a scalar G, not related to G dot. This is just a scalar yield function. This is the tensor of that describes the plastic part of the deformation. And when the distortion of the lattice, then the idea is that when this distortion of the lattice reaches a threshold, then yield begins, and we can have a change in the plastic deformation. Okay. So that defines a surface in 6-dimensional space, strain space. Now, we stipulated before that in real metals, the elastic strain is invariably very small. That is to say, the material will yield or it'll reach this threshold at a small value of elastic strain. Under those conditions, the elastic strain, this again is the strain based on the intermediate configuration as the reference configuration, that and the second Piola-Kirchhoff stress, also based on the local intermediate configuration, they're in one-to-one relationship with each other. Okay. So in other words, we had this, for small elastic strain, we have the second Piola-Kirchhoff stress relative to the intermediate state, or some fourth order tensor of elastic moduli operating on the elastic strain. This is the usual classical elastic moduli. And we can invert this to write the strain as a function of stress, and this L here, we call those the elastic compliance tensor. And so this C and L are inverses of each other, effectively, in the 6-dimensional vector space of symmetric tensors. So because of that, we could recast the yield function in terms of S. We could write G of E as some function of S, where that function is G with E given in terms of S in this manner. Okay. Okay, so the motivation for this goes back to day one of the course when we talked about uniaxial test and the notion of yield. We plotted the uniaxial Cauchy stress in an axially loaded bar against the strain, which we took to be the natural, so-called natural strain, or the natural log of the stretch. And for small values of the stretch, this is approximately lambda minus 1. Sorry, for small values of the strain, I should say, this is, well, I don't want to say that at all, actually, because epsilon could be quite large. We're just talking about the elastic part at the moment, which is invariably small in practice. Okay, so that plot exhibits this kind of nice symmetry in tension and compression. And the takeaway here is that the stress can never rise above the yield value, but the yield value may itself evolve post-yield, after the initiation of yield. With continued deformation, the value of the yield stress itself could conceivably change, but the stress can never rise above that value. Okay. So the idea is that yield is characterized then when, say, the absolute value of stress is equal to a yield value. We'll take it in our preliminary stage of our discussion, we'll take this to be a constant. Later on, we'll talk about strain hardening, which is this phenomenon here where the yield stress changes with continued deformation. So this is the analog of this equation here. Some function of the 3D stress is 0. Well, in the one uniaxial case, that function would be like absolute value t minus t sub y equals 0 defines yield. Whereas elastic response then is associated with absolute value of stress less than the yield value. Extrapolating to the general 3-dimensional situation, we could say then that f of s equals 0 then defines this surface in 6-dimensional space. Of course, we can't visualize that, but here's a 3-dimensional analog. Or actually, worse than that, it's a 2-dimensional analog since we're on the 2-dimensional page here. The elastic range corresponding to this regime here is associated, say, with f less than 0, which means absolute t minus ty would be less than 0. That's the analog here. We'll call that the elastic range of response. Absolute t greater than ty is impossible physically. That will correspond to the exterior, let's say, of this elastic range. We'll call that f, the region where f is greater than 0. That's inaccessible because no state of stress can exceed yield. Okay? And here in this experiment, the state of 0 stress here, state of 0 stress is within the elastic range as we've defined it. So we'll assume similarly that the point s equals 0 is contained inside the elastic range. And we'll revisit that later in the course when we talk about not only hardening, but also the so-called Bauschinger effect, which is associated with a differential response in tension versus compression, which may be so severe that by the time you reach 0 stress, you've actually yielded the material again before you get there. So this assumption is typically satisfied, but there may be extreme circumstances in which we would have to generalize this assumption here. So we'll come back to that a little bit later in the course. Okay, so that's our basic notion of yield. So we started with the idea that yield happens when the distortion of a lattice, let's say the elastic distortion then, is sufficiently severe, which means the elastic strain is sufficiently severe. Combine that with the empirical fact that the elastic strain is invariably small, so that it's interchangeable with S, second Piola-Kirchhoff based on the intermediate state. And that then gives us a framework in which to characterize yield. We'll come back to the yield function. So this function f of s, just like g of e, is a constitutive function. We've already arranged it to be invariant under superposed rigid motions. We also need to invoke, say, material symmetry restrictions, because after all, the yield function characterizes the material at hand, and so it's subject to the same material symmetry restrictions that we invoked earlier in discussing the strain energy function, for example. Okay, back in the beginning of the course, we talked about the idea of a closed cycle of deformation, and we used that idea, a work inequality for a closed cycle. We use that to deduce that there exists a strain energy function, so-called that's the basis of hyperelasticity, so-called. And that was kind of a quasi-thermodynamic argument in the sense that it's not dictated by thermodynamics per se, but it's sort of inspired by thermodynamics. And in particular, it means that perpetual motion machines are impossible. In other words, to create a cyclic process, you have to supply work to the material. You have to exert power from some external agency, from the forces that are applied, in order to produce a cyclic process. The alternative would mean you could generate energy indefinitely just by cycling a material, and that's contrary to our everyday experience. If we could do that, then there'd be no, we'd have an out of control supply of energy in the world, and that's not the case. So let's revisit that discussion. So we suppose we have a cyclic process in some interval of time, t between t1 and t2, and I'll call that interval I. What we mean by that is the deformation at every point in the body is the same at the beginning and the end of the cycle. And the velocity is 2. We'll suppose that we're clever enough to design experiments that can make a deformation return to its initial value at time t1 after the end of the cycle, namely at time t2, and also the velocity. So that's a hypothetical idea, because doing that in practice could be quite difficult unless you could arrange the deformation to be homogeneous in the body, in which case controlling the boundary values of the deformation would mean you have control over the interior values as well. If the deformation is non-homogeneous, then you would not, then merely controlling the boundary values of the deformation would not control the interior values, right? So implicitly here, to do this experimentally, you would be talking about homogeneous deformations in practice. Okay, so if we take the gradient of this top line here, that means the deformation gradient begins and ends at the same values as well. And I'll henceforth suppress the reference to the explicit material point, capital X, because the discussion to follow, most of it will be taking place at a fixed material point. Okay, so if you recall mechanical power identity, we've used repeatedly, the power of the forces applied to, say, a subvolume pi of the reference configuration is the rate of change of kinetic energy for that fixed set of material points, plus the stress power. So if we want to compute the work done by these forces in the cyclic process, in this time interval I, I'll call it W sub I, associated with the material region pi, that would just be the integral between the two times at the beginning and end of the cycle of the power of the forces. Use this, and we just get the kinetic energy at the two times subtracted. But with the velocities the same at the beginning and end of the cycle, these two kinetic energies will be equal, and so the difference will drop out. And we'll just get the time integral of the stress power. And assuming the integrand here is continuous in space and time both, then we can interchange the order of integration. And that gives us then an expression involving the integral over pi of the time integral, p dot f dot, then integrate that over the volume. So our assumption will be that to create such a cyclic process, we must expend positive work or non-negative work on any subregion of the body that's undergoing a cyclic process. And we've seen this before back on beginning of the course, pages 13 and 14, right? So we've seen this discussion before. This is a review. If this is non-negative for all subvolumes pi, then the integrand here, which is the time integral, must be non-negative at every material point. Okay, so we've seen that before, and in the case of pure elasticity, that led us to conclude that there exists a strain energy function. This time, let's suppose that our cyclic process is such that it starts out in the elastic range, and it ends up there too, but there could be a subinterval of time, say time TA to TB, during which the process impinges on the yield surface so that plastic flow is possible in that subinterval of time from TA to TB. Okay. So that's the difference from what we've done at the beginning of the course in talking about pure elasticity. Pure elasticity would mean a cyclic process which is such that we never encounter the yield surface. We're always within the elastic range. So that's included here as a special case, right? You could always select such a cyclic process. Okay, so if this is the case, then for this cyclic process, we can have plastic evolution, that is k dot, could be non-zero, only in that subinterval of time between time A and time B. So that means the plastic deformation at time t1, it doesn't change until you encounter time ta. So K at T1 is K at TA, and likewise K at T2, between T sub B and T sub 2, there's no plastic evolution, so K remains fixed. K at T2 is K at T sub B. Okay, so we want to impose this inequality then. This discussion now pertains to a fixed material point. Okay, the whole discussion here, henceforth. If you look back at what we've done recently, the stress power was the time derivative of this referential energy density, given here in terms of our W of H is Fk, of course, plus the dissipation. So when we integrate P inner product F dot, we're going to be integrating psi dot between those two limits, T1 and T2, which will give us psi at T2 minus psi at T1, and then the time integral from T1 to T2 of D, the dissipation, which remember is epsilon inner product K dot K inverse. The K dot is 0 except during the subinterval of time TA to TB, subinterval of the interval T1 to T2. So the integral, this last integral from T1 to T2 is really just an integral TA to TB. Let's look at this first term, the energy. So psi is a function of F and K via this definition. So we have F at T2, which is F at T1 because we've stipulated this is a cyclic process, which brings the deformation bracket to its initial value. K at T2 is K at TB minus psi evaluated F at T1, K at T1, which is K at TA. So the only thing that's changing in the argument of psi here, this F is not changing, it's the same F. Only K is changing. So this difference is the same as integrating the psi dk inner product K dot between the limits TA and TB, right? Because the first argument F is the same. Okay. All right, so we've reduced our dissipation inequality to this, or our work inequality, I should say, to this statement. Okay, well, I could imagine a cyclic process in which TB approaches TA so that we only encounter the yield surface for a vanishingly small interval of time. Let's look at this, and the limit then is TB approaches TA. Of course, TB is larger than TA, so that's going to be positive. What we can do is we can divide this by TB minus TA. That would give you the mean value of the integrand during the time interval TA to TB. And then pass to the limit as TB approaches TA. Right? That, in that case, we know from the mean value theorem, assuming the integrand here is continuous as a function of time, we know that the mean value will correspond to the integrand itself for some time within the interval. And as TB approaches TA, then the mean value approaches the integrand evaluated at TA. Okay, so that gives us this inequality. F is at T1, K is now at TA. K dot is evaluated at TA, and we have the dissipation at TA. All that should be non-negative. We're not quite done here with this because we stipulated that the cycle not only begins in the elastic range, but also ends there. How can we be sure that that's true? Well, this passage to the limit TB going to TA actually ensures that, because, for example, if we start in the elastic range, then the yield function scalar, this is not a tensor, scalar F at S at T1, that's inside the elastic range by assumption, because T1 starts in the cycle starts in the elastic range. H at T2 would be F at T2, K at T2. K at T2 is K at TB. F at T2 is F at T1 because of the cyclic nature of the process. So we have this. TB is approaching TA, and if K is a continuous function of T, that means K at TB is approaching K at TA, which is K at T1. And then ultimately then, so we have H at T2 is approaching H at T1, which means the elastic strain at T2 approaches the elastic strain at T1. So the associated second Euler-Kirchhoff stress also coincide in that limit, which means F at S2, F at S at T2, which is F at S at T1, which is negative. So indeed, the cycle also ends in the elastic range as we assumed. So everything's consistent. Okay, so we like to translate this inequality here into something useful. Let's look back on page 81 of the notes. We went to the trouble of computing the derivative of the energy with respect to K. And this is now the place where we use that result. That was minus our Eshelby tensor at the same arguments, F at T1, K of T, times the inverse transpose of K at sine T. So refer you back to your notes for that. And also, so this derivative, decide decay K dot is minus epsilon K inverse transpose K dot. We also spent some time to establish that that's the same as the inner product of epsilon with K dot K inverse on page 92. And if you look back at our expression for the dissipation then, previously, which also involved a K dot K inverse, we reduce that inequality, of the work cycle inequality, to this statement. The Eshelby tensor associated with the state on the yield surface at time TA minus the Eshelby tensor associated with the state at time T1, the beginning of the cycle, when we're in the elastic range. Inner product K dot K inverse at time TA, so this is tensor K, is non-negative. If you look back at the definition of dissipation, this means that the dissipation is actually maximized by the state that lies on the yield surface at time TA when the yield function is 0. Maximized relative to the state at the beginning of the cycle, which lies within the elastic range. Okay, so a very common assumption in plasticity, invoked almost universally and has been around almost as long as the subject of plasticity itself, is that the state at the yield surface, the state of the material at the yield surface, is such as to maximize the dissipation relative to any other state. So here the K dot is always associated with plastic evolution taking place at time TA, but it's the state at the yield surface maximizes the dissipation. And this is a justification. Everything we've done here so far is a justification of that hypothesis based on the very plausible notion that non-negative work is required to produce a cyclic process. Okay. So this is great. This is interesting. However, it's not especially convenient. A more convenient formula or inequality can be had by using the Eshelby tensor epsilon prime that we had before on page 92, which was based on the intermediate state as the reference. Remember, this epsilon was a referential tensor based on, it's got both legs, if you like, in the reference configuration. We recast the dissipation inequality in terms of an epsilon prime with both legs in the intermediate configuration. And then we juggled around with the trace definition of the inner product to rewrite this K dot K inverse in terms of the epsilon prime Eshelby tensor and K inverse K dot. And we can translate this inequality then by using that epsilon prime. And epsilon prime, now, the reason that's useful is because it's expressible entirely in terms of the elastic strain. So here I'm writing epsilon prime as a function of the elastic strain. The basic definition, if you recall, was our W of H, the elastic part of the deformation gradient, times identity minus H transpose dW dH. The W at H is the same as U at E, that's the strain energy expressed as a function of strain. And dW dH was itself H times S, a function of E. H transpose H then comes from here. That's the elastic Cauchy-Green deformation, which is identity plus 2 times the strain. So that this epsilon prime Eshelby tensor is expressible entirely in terms of the elastic strain. And our work inequality then says that epsilon prime associated with the elastic strain that impinges on the yield surface maximizes the dissipation relative to an epsilon prime associated with the state of strain lying within the elastic range. Okay, that's still a little bit unwieldy. A cleaner formula can be had if we use the fact that under our small strain hypothesis, small elastic strain hypothesis, the elastic strain and S are interchangeable, right? So we can write the elastic strain in terms of S by using the compliance tensor. We put that in here, and we have an inequality involving the stress. And the conclusion then is that the dissipation is maximized by those stresses that lie on the yield surface, Fs equals 0, relative to all other possible S's, namely S's that are such that F is less than or equal to 0. F greater than 0 being impossible. Okay. Something to note from this prediction here, this result. If the elastic strain is the identity, which means, of course, no distortion of your lattice, let's say in the case of the crystalline solid, then our strain energy, which is quadratic in the elastic strain, vanishes. Under our hypotheses, the stress also vanishes. That means this epsilon prime, everything is 0 on the right-hand side in this case, is 0. If you go back to the definition of dissipation in terms of epsilon prime, that's also going to be 0 in this case. And remember our hypothesis we introduced that the only way to have dissipation is if K dot is non-zero and vice versa. The only way to have K dot non-zero is if the dissipation is positive. Well, here we have a 0 dissipation under this assumption. That means there's no plastic evolution. So there can be no plastic evolution without elastic distortion, that is to say, without stress. And that's very much in line with what is observed experimentally. A material will not spontaneously yield unless there's stress in the material. Okay, so let's, what I want to do is get a more useful form of this inequality by invoking our small elastic strain assumption and approximating that inequality for the case of small elastic strain. Okay, small elastic strain, or strain energy is quadratic. Here are the elastic moduli, fourth order tensor. It's not exactly quadratic, but there's an error of order small o norm e squared, right? So that the whole thing is small o of norm e, and small o means any term that's smaller than norm e as norm e gets small. So this, in other words, this is quadratic and higher order terms, and that's certainly smaller than any term of order e itself. We also have here, sorry about this, identity plus 2e times the stress. For small elastic strains, the stress is already linear in E. So this whole thing will be I times S plus 2e times S. We need to approximate that to leading order for small strain, right? That's just this. S is C plus a small error. Multiply this out, you get C plus quadratic terms. Those are small o norm E. And then this is just our S, right, at leading order. So the epsilon prime tensor, if you want to approximate this to leading order, epsilon prime to leading order in the small elastic strain, U is too small to worry about. It's quadratic, whereas S is linear. So this S contribution dominates the energetic contribution, right? So with the minus sign here, we find that epsilon prime is approximated at leading order by S itself, minus S. Right? And then we make an error that's negligibly small because the elastic strain is such. Okay, well, we could get rid of the minus sign in our work inequality by just noting that K inverse K dot is the same as minus G dot G inverse. To get this, you just differentiate G times K equal to the identity because G and K are inverses of each other. And you'll immediately deduce this. And then, so wherever we say K inverse K dot, we can replace it by minus G dot G inverse. And the minuses will drop out. And we can rewrite our work inequality in this more classical form, actually. This is the form you see in classical plasticity. Now, in the meantime, there's a sleight of hand here. The Eshelby tensor, there's no, in general, for example, you have here that this term is symmetric, and of course S is symmetric and E is symmetric, but E times S is not symmetric. It is symmetric in the case of an isotropic material, it turns out, but not in general. So epsilon prime has no particular symmetry. Okay. However, having now approximated it by minus S in the small strain limit, small elastic strain limit, epsilon prime is then approximated by a symmetric tensor. So the inner product here will only pick up the symmetric part of the factor on the right, right? Because you can decompose any tensor into the sum of symmetric and skew parts. The inner product with some other symmetric tensor will annihilate the skew part. And that's what we've done here. I've inserted this qualifier, sim, to stand for symmetric part of G dot G inverse, because this factor in square brackets is now symmetric. So although I could leave it as G dot G inverse, the fact is the inner product will annihilate all but the symmetric part of G dot G inverse. It'll annihilate the skew part, okay? So the work inequality implies this very important inequality that involves the plastic evolution G dot. It says that if S lies on the yield surface, then it makes an inner product with the symmetric part of G dot G inverse, which exceeds that made by any other admissible S star, let's say. S star not exceeding the yield limit, whereas S itself is on the yield surface. And you can see geometrically what that implies. So for example, so here's a point on the yield surface. Take any other S star in the elastic range, whatever shape it has. Okay? It has to make an inner product with symmetric part of G dot G inverse that's non-negative. So you can see is, if you draw the arrow, S minus S star would be this, for example, as S star is here, S minus S star is that arrow. It's just a vector. It's a six-dimensional vector, but we can imagine it in this graphical way. If it's going to make a non-zero inner product with symmetric part of G dot G inverse, then that symmetric part G dot G inverse has to be perpendicular to the tangent plane of the yield surface at the point S. Right? Moreover, this kind of situation here would be impossible. For example, if you had a yield, an elastic range that was like this, it sort of looked concave, it had a dimple like this. You pick an S star over here, S minus S star would make a negative inner product with this symmetric part of G dot G inverse, which would violate this inequality. So this is a very important inequality following only from our work inequality that we introduced. First thing is it says it implies that the symmetric part of G dot G inverse must be perpendicular to the tangent plane to the yield surface itself. So it has to be perpendicular to the yield surface. And the entire elastic range must lie to one side of the tangent plane. So this is admissible over here. The entire elastic range is on one side of that tangent plane. Whereas here, you've got part of the elastic range on one side, below, and other parts above. This situation would be inadmissible because it would produce an inner product S minus S star, which violates this inequality. So this would not be admissible. This part B in this figure would be not allowed by the work inequality. It stipulates that the elastic range, the region F negative, must lie entirely to one side of the tangent plane to the yield surface at any point on the yield surface. Okay. That has important mathematical consequences. That means, for example, if you take any 2 points lying in the elastic range, you can connect them by a straight line, and every point on that straight line will also lie in the elastic range. So that's true here, for example. This point and this point, they both lie in the elastic range, and every point on the straight line between them also does. That's not the case here, right? In this part B, which is not possible, here's a point in the interior, here's a point in the interior. If you connect them by a straight line, then not all points on that straight line, there'll be some that are not within the elastic range. Again, that's not possible. So such a set, the elastic range defined that by this property, that's called a convex set. And the definition, so it's a convex set in our 6-dimensional vector space, that is stress space. So this has the property that if you have 2 points, S1 and S2 inside the elastic range, you construct a straight line path connecting them, that's given by this, where U is any parameter between 0 and 1. So when U is 0, you're at S2. When U is 1, you're at S1, let's say. And this is a linear function of U, so that's a straight line in between S1 and S2. So every point on that line satisfies this inequality. And so every straight line is within the elastic range. Okay, so it sort of begs the question now, what happens if the yield surface has a corner in it, where then the tangent plane becomes ambiguous, right? If it has a corner, if it's like a faceted surface, like this, so you encounter some point on the yield surface, and you don't know what the normal is, right? Well, you could think of such a surface as the intersection of smooth yield surfaces. So we extend this one smoothly using this dashed line and intersect this one smoothly using that dashed line. But then the actual yield surface is the intersection of those two. The normal to this one, this smooth yield surface, is no problem. It's unambiguous. The normal to this yield surface is also unambiguous. But at this point, the normal is ambiguous. It could be any direction within the so-called fan of normals between these two extremes. So that's the situation that we would encounter if we had a yield function that had corners in it. Such a yield function, by the way, is is exemplified by the so-called Tresca yield criterion. You've all heard of the von Mises yield function and also the Tresca yield function, which are widely used in the case of isotropy. So the Tresca yield function would give rise to an ambiguity in terms of this, the direction of this G dot G inverse. We'll see in a moment, though, that our framework that we're discussing here will lead us automatically, actually, to a smooth yield function, as we'll see. However, if the yield surface is smooth, that means that the function f of s is differentiable. Its tangent plane will be continuous with no corners. So if you have a smooth surface, you can always define an unambiguous normal to that surface. So think of this as just, for example, a surface in 6-dimensional space, the analog of an ordinary surface in 3 dimensions. You know that in 3 dimensions, the exterior normal to the surface is in the direction of the gradient of that function with respect to, say, position in 3-dimensional space. Well, the same is exactly true in here without change. The same argument exactly gives us that the exterior normal to the yield surface lies in the same direction as the gradient of the yield function with respect to its argument, stress, the derivative of f with respect to the stress. Okay, so we'll interpret this derivative as a symmetric tensor. Because we would calculate it using the chain rule, f dot is df ds inner product s dot. And because s dot is symmetric, it's only the symmetric part of this gradient that matters. And so we could define it a priori to be a symmetric tensor. Okay. So we know in the case of a smooth or differentiable yield function, Tresca is not differentiable with respect to s at every point s. But in the case of a differentiable one, we then can say something definite. The symmetric part of G dot G inverse, first of all, it's in the direction of this gradient, so there must be some scalar multiplying that gradient, which gives us symmetric part of G dot G inverse. Furthermore, we can say that lambda is non-negative because symmetric G dot G inverse must point in the same direction as the exterior normal. So in the same direction as this. If lambda were negative, then this would point in the opposite direction to the exterior normal. So we can stipulate then that there must be some lambda. Lambda could vary with material point and the time also, because in this whole discussion, remember we froze the time at t sub a, right? T sub a. Well, that time could be arbitrary, right? So at any different time, there would be a different TA, and at any different material point, there would be a different lambda. So lambda could depend on the material point and the time. That lambda has to be determined in the course of solving a given problem and a given initial boundary value problem. And so this lambda emerges as a kind of Lagrange multiplier. It's often called the plastic multiplier. Unlike ordinary Lagrange multipliers, however, it has a definite sign. Okay? That definite sign is associated with this restriction. Let's back up a bit. This restriction that it's not any S star that is involved here. S star must be such as to satisfy this inequality constraint. And it's that inequality constraint that gave rise to a Lagrange multiplier with a definite sign, non-negative. Okay. By the way, the same result follows if you studied optimization theory. It's exactly the same as the so-called Kuhn-Tucker necessary condition of optimization theory. The optimization problem in this case is to maximize this dissipation with respect to S, right? We're comparing these two S's here in this inequality from before. We're comparing two S's. we're maximizing with respect to S, subject to a restriction, an inequality constraint, that S has to not violate the yield condition. In other words, you cannot have an S for which F is positive. So if you look up Kuhn-Tucker necessary conditions in optimization theory, you would immediately get, by the way, there should be a symmetric part here inserted before G dot G inverse, but the inner product only picks up the symmetric part anyway. You would immediately get this condition with this restriction on lambda. So this is called the flow rule. It tells us, given the yield function and the state of stress, it puts a restriction on the manner in which the plastic evolution can change in time. So that's, a major key to unraveling the mystery of plasticity, is to figure out how the plastic evolution evolves. Okay, so in our flow rule, the symmetric part of G dot G inverse was lambda df ds. G dot G inverse then is this symmetric part plus a skew part that we know nothing about at this stage. Okay, that skew part we'll call the plastic spin, because this looks an awful lot like conventional continuum mechanics. For example, F dot F inverse would be the spatial velocity gradient, L. We can decompose that into a symmetric part and a skew part, the spin tensor. So we'll call this omega, the plastic spin skew tensor. So in principle then, we need not only a yield function, but we need some constitutive function for the so-called plastic spin. We can imagine, for example, the plastic spin can also depend on S and perhaps other variables that are relevant. Okay, and it's only activated when, of course, G dot is non-zero, when there's yield. We'll come back to this plastic spin. By the way, plastic spin was a real headache in the up to recent times in the development of sort of modern plasticity theory. There'd be many papers arguing back and forth about whether plastic spin was a real thing, or whether we could dispense with it, or whether we really had to worry about it. There was quite a literature back and forth, mostly to no effect. And I think the reason is, when people were discussing plastic spin, they forgot to incorporate notions of material symmetry in the discussion. And we will do just that in a little while here, when we segue into the subject of isotropy. Okay, let's say something about material symmetry. So this F, this yield function in particular, is a constitutive function, as is omega, by the way. So they're subject to material symmetry restrictions, just like the energy and the stress, right? If you look back at pages 68 and 69, when we talked about material symmetry, we stipulated that U of E, the strain energy as a function of the elastic strain, should satisfy U at E equals U at R transpose ER, where R is any element of the symmetry group relative to the intermediate state. So that was a subset of the proper orthogonal group. But because R occurred quadratically in that restriction, we could extend this set to the full orthogonal group, right? So it's some subset of the set of all orthogonal tensors. We showed back on these pages, that was a while ago by the look of it, that the stress then satisfies this restriction. If you take the stress evaluated at E, the constitutive function for the stress, and you replace E by R transpose ER, where R is an element of the symmetry group, then what you get is S hat at R transpose ER is R transpose S hat at E times R. We care about this because our yield function could depend on E or S. So we'll see what this implies. Okay, so remember now we're talking about small elastic strain. S hat at E is this linear function, and it's invertible. In other words, we could write the strain as some tensor E hat, should be an underline here, E hat of S, which is the compliance tensor times the stress. And these are inverses of each other, which simply means if you take any symmetric tensor A, operate on it with C, you get something, then operate on the result with L, you get the original A back again. That's what it means for these C and L to be inverses of each other. And by the same token, if you operate on A with L and then take the result of that and operate on it with C, you'll get A back again. And we care only about symmetric tensors here because both C and L have this property of minor symmetry, which annihilates any skew part of A. Okay. So let's see. This equality above, which we derived some time ago, plug in place of E, plug in R transpose ER, you get this. C operating, fourth order tensor operating on R transpose ER. You get this R transpose C at E times R. So this is the restriction that has to be satisfied by our fourth order tensor of elastic moduli for any strain E, right? R is some set of specific R's associated with the symmetry of the material. Put in any E you want whatsoever here, any symmetric E, and this C must be such as to satisfy this restriction. So that places a restriction on the fourth order tensor of elastic moduli. Okay. So, and this is the reason why different types of materials, different crystal classes have different elastic moduli tensors. Not only the numerical values, but the non-zero entries differ from one class of crystals to another. Let's have a look at what happens to this function when we replace S by R transpose SR. Okay. So the compliance evaluated R transpose SR. Well, R transpose SR, let's see. This here is R transpose SR. So that would sit here. But if we use this equation, we immediately get that that's C at R transpose ER, right? And then use this result to assert, well, because L and C are inverses, that must just be R transpose ER. So by the way, as a parenthetical remark here, since E is LS, we could put that in here. And we see that the compliance tensor satisfies exactly the same symmetry condition as the modulus tensor. That is, L at R transpose SR is R transpose L at SR. The same structure as the compliance tensor. Okay? So we have this result. In other words, R transpose, if we use E hat at S here, R transpose E hat at S times R is equal to the compliance operating on R transpose SR, but the compliance operating on R transpose SR is just E hat at R transpose SR. So we have a formula that's entirely analogous to this top one. R transpose SER is the same as S at R transpose ER, and likewise, conversely, E hat, the constitutive equation for the strain as a function of stress, satisfies E hat at R transpose SR is R transpose, tensor R transpose, E hat SR. Well, why does any of that matter? Well, we need this to narrow down the possibilities for the yield function due to material symmetry. So for example, if we write the yield function as a function of strain, then because this is a constitutive function, just like the strain energy function, it must respect the symmetries in the material, right? So G at E must be G at R transpose ER, where R is any element of the symmetry group. Okay, well, we can write E as a function of S, as we've just indicated, and that tells us, that gives us a yield function that depends on the stress S. we carry that here. What we've just seen is that R transpose E hat S, R, is E hat at R transpose SR. We put that in here. But from this equation, from this line, if you replace S by R transpose SR, then you have to do that consistently here. E hat at R transpose SR is the same as F with S replaced by R transpose SR. So the yield function expressed as a function of the stress satisfies exactly the same symmetry restriction for the same set of R's, the R's that associate with the symmetry group, with the material. Okay, so that's important because in virtually the entire subject of plasticity, I would say 95% of it, the yield function is always expressed as a function of the stress. So it's essential in classifying different materials to know the symmetry group. Otherwise, you might write down a yield function that's not appropriate for a particular material symmetry. And people have done that over the course of the history of the subject. And I think the reason is a good understanding of the notion of material symmetry came much later in the history of the development of continuum mechanics. Long after ideas like plasticity were first introduced. And so the bridge between the old ideas and new ideas in plasticity really, I think, is built largely on the notion of material symmetry. So it's really important to understand material symmetry in this subject. Okay, just to refresh your memory, if we let E bar, let's say, be R transpose ER, where R is an element of the symmetry group, then we have that U at E bar is U at E, right? That's just a restatement of the material symmetry condition for the strain energy function. And it's this condition that we used way back on page 68 to prove this top equation here at the top of this page. Namely, we use this restriction to prove that the derivative of the energy with respect to E bar is R transpose times the derivative with respect to E times R, which means that the constitutive function for the stress evaluated at E bar is R transpose constitutive function for the stress evaluated at E times R. And that's the equation we had at the top of this page. Well, we're going to, in our flow rule, we have to differentiate the yield function with respect to the stress. So we can simply invoke the same result. If we let S bar equal R transpose SR, then we have F at S bar is equal to F at S. We could differentiate as we did way back on page 68 and get that the derivative of F with respect to S bar is R transpose the derivative of F with respect to S times R. And that kind of innocuous result turns out to be really important. Before we go further in this discussion, let's make a further simplification, which is based on very famous experiments on metals carried out by somebody named Bridgman at Harvard University in the early 1950s. And if I'm not mistaken, Bridgman actually got a Nobel Prize for this work. He was looking at the high pressure behavior of metals. And what he discovered in the lab, I mean, he was able to achieve pressures that were unheard of, exceedingly high pressures, much higher than any metal would experience in normal engineering service. What he found was that yielding is essentially insensitive. I said approximately here insensitive to pressure, up to exceedingly high pressures. So in other words, if you just take a chunk of material and pressurize it, it won't yield just due to pressure alone. You have to do something else. You have to shear it, for example. So pressurize a state of stress that involves a pure pressure will have no measurable effect on the yielding of the material. So you have to have some deviatoric component to the stress to make it yield. Let's see what that implies for what we've done so far. So let's incorporate we've incorporated basically two experimental observations so far in the development of the theory. One is that the elastic strain is always tiny. And secondly, now Bridgman's observation that yielding is insensitive to pressure. So we should embed that notion into our yield function. Our yield function is insensitive to pressure. Pressure is 1/3 the trace of T, or minus 1/3 the trace of T. So yield function should be insensitive to the trace of the stress. The yield function, however, depends on S, not on T. So we have to connect S and T. Remember, S, the second field of Kirchhoff relative to the intermediate state. To get to the current state, you use H, from the intermediate to the current. So this is just the usual relation between Cauchy and second field Kirchhoff using the intermediate state as reference. Here's determinant H and HSH transpose. Let's look at the trace of this expression. Trace is a linear operation, so the trace of the scalar times T, the scalar just comes out in front of the trace. We have the trace HSH transpose. The trace is nice. You can interchange any of the factors without affecting the result. So we can put the H transpose in front, right, without affecting the result. H transpose H is the elastic Cauchy-Green tensor, which is identity plus twice the elastic strain times S. The stress is linear in the elastic strain, approximately. Expand this out, you get S plus the quadratic term in the elastic strain. Take the trace of that, you get trace of S plus small o of the elastic strain. Okay? And also, determinant of H, let's see, the square of that is the determinant of H transpose H. You can write H transpose H as identity plus 2E, expand the determinant, and you'll find, I'll leave that as an exercise for you, you'll find that the determinant of H is simply 1 plus the trace of E, this E, plus higher order terms. If you divide that, the reciprocal of that would be 1 minus the trace of E plus nonlinear terms, right? And you multiply that by this and retain terms at leading order in elastic strain, you just get the trace of T is the trace of S plus negligible terms in the elastic strain. So at leading order, the trace of T equals the trace of S at leading order in the elastic strain. So if we incorporate Bridgman's observations into our theory, combine that with the notion of small elastic strain, F then, our yield function, should be insensitive to the trace of S.
Were these just compressive pressures in these tests? Was it like
I suppose you could induce vacuum. You can't get lower than vacuum, right?
Yeah. In
the laboratory. So I would think, I mean,
I was thinking like tension test, but with
that you need look up his experiments. But yeah, that's a good question. I can't quite recall what the experiments entailed, but so yeah, I mean, I don't know if he was able to achieve a state of severe triaxial tension or not. Severe triaxial tension. But I mean, if you look at our original uniaxial curve, for example, where you have, if you plot the stress against logarithmic strain, you have tension compression symmetry, right? Then I would think that Bridgman's compression experiments would also apply to tension for the same symmetry. But have a look at, that's a good thing to look at. In fact, let me stop here and say for a moment, start thinking about your course projects. That should be a 20-minute presentation at the end of the semester. And investigation of experiments, famous experiments like Bridgman's, for example, would certainly be a worthy presentation to tell us about, if anybody's interested. Okay, so the conclusion here then is that our yield function as a function of S should be insensitive to the trace of S. Well, what's left over after the trace is the so-called deviatoric part of S, which you've all heard about in continuum mechanics. So we could stipulate that the yield function should depend on the stress then through its deviatoric part. I'll call it DEV, D-E-V. That's defined this way. Just take stress, subtract 1/3 the trace of S times the identity. Okay. This is useful because if you write S as dev S plus this part proportional to the identity, the two parts are orthogonal to each other in the sense of tensor inner products. The inner product of any deviatoric tensor with the identity, that would be the trace of the deviatoric part, is identically 0. That's how the deviatoric part is defined. So that's a nice way to decompose a tensor. Another nice way, of course, is as a sum of symmetric and skew parts. This is also an orthogonal so S as dev S plus 1/3 trace S identity. That's another orthogonal decomposition of a tensor. Orthogonal in the sense of the inner product of tensors. Okay. We stipulated that our yield function should satisfy this material symmetry restriction involving R. Let's see what that implies for F tilde as a function of deviatoric S. First of all, if you replace S by R transpose SR, as stipulated in the material symmetry restriction, you get R transpose SR minus 1/3 of its trace times the identity. In the trace, you can put the R in front of the R transpose. That gives you the identity because R is orthogonal. So you just get trace of S, or trace of S itself. And you can write the identity as R transpose R times with the identity in between. So you get R transpose times the deviatoric S times R. So that tells us something useful. F tilde of deviatoric S, which is the yield function satisfies this material symmetry, which says that if you replace S by R transpose SR, you don't change anything, provided R is an element of the symmetry group. That means replacing here S by R transpose SR in this deviatoric operator. But because of this result, that's the same as replacing deviatoric S by R transpose deviatoric S times R for all elements of the symmetry group. Okay. I think I'm about to end here, but we will use this to great advantage in our discussion of isotropic materials starting next time. Okay. So yeah, this is a good place to stop, and I'll just pick up isotropic materials. This is where I would say 90% of the entire subject of plasticity historically resides, under the heading of isotropic materials. Almost all of the literature is devoted to isotropic materials. A lot of research papers on anisotropic plasticity, crystal plasticity, but those are much more recent. The vast majority of textbook applications and others covers the isotropic case. The reason is that this is, of great utility in engineering calculations, because engineering metals are polycrystalline invariably, and the polycrystals are more or less randomly oriented. So although each grain is crystalline, after you randomly orient the grains, you have what appears macroscopically, at least, to be a roughly isotropic material. So the isotropic theory is the subject of virtually all textbook treatments of plasticity. We'll discuss it at length, and we'll also later talk about crystalline plasticity. So let's stop here for today, and we'll pick up the isotropic theory later. And we'll use, in fact, material symmetry arguments to show that we can dispense with nuisance terms like the plastic spin, which otherwise we would have to give a constitutive equation for the plastic spin. it turns out that in the case of isotropic materials, we can use material symmetry to dispose of the plastic spin, to neglect the plastic spin altogether without any loss of generality. Okay, so we're headed to that next time. Are there any questions?
Can I ask you a question?
Yeah.
As we described before, this insensitivity to pressure for the yield function, does it insinuate that when you just apply pressure, your material never yields?
Essentially, yeah. I mean, you can. This is experimentally true for experimentally feasible pressures.
Yeah.
I mean, if you apply pressure using a nuclear bomb, for example, then
yeah,
you may get some yielding, right?
Yeah. For instance, if I just throw an object to the bottom of the sea, it won't fail.
No, it won't. It won't yield. Well, it may do something else, but according to Bridgman, it won't yield. Yeah.
Therefore, we might just have fracture, for instance, but no plastic deformation.
According to the experimental record, yeah.
Okay.
And I mean, that's sort of consistent also with our beginning interpretation of plasticity in terms of dislocation motion, which causes a crystallographic slip.
Yeah.
Which overall produces a kind of macroscopic shear deformation.
Yeah.
Which doesn't entail any volume change, and so you wouldn't expect pressure to play a significant role.
Yeah.
So that's indeed what Bridgman has found. So all of the classical theory and almost all of the research literature invokes this assumption. Yeah.
Okay.
Any other questions? Okay, then in that case, I'll see you tomorrow evening and on Thursday.
Thank you.